The Airborne
Front,
Science Office is
left,
located at
front,
NASA's
right,
Ames Research Center
front,
south of San
right.
Francisco. The Airborne
Front,
Science Office is
left,
located
front,
at NASA's
right,
Ames Research Center
front,
south of San
right.
Francisco. The Airborne
Front,
Science Office is
left,
located
front,
at NASA's
right,
Ames Research Center
right.
south of San Francisco.
funciona bien? ¿Este funciona? Sí. Ok. ¿Este funciona bien? ¿Este funciona? Sí. Ok.
Okay, I think we now are ready to start. Sorry for the for the delay. So today we have Alex Borlaff. He's an ex-student of the IC. Some of you know him. He did his thesis here with John Beckman. Then he was at the I think we European agencies. Sorry for the delay. So today we have Alex Borlaff. He's an ex-student of the IC. Some of you know him. I think he did his thesis here with
Maybe
John
you-
Beckman. Then he was at the I think we European agencies. Sorry for the delay. So now that's perfect. Okay. So I think now you will don't hear me up twice. Okay. So he afterwards he moved to NASA to do a postdoc there, and now he's also a research there until at least 5 more years. And now today he will talk about airborne astronomy and a little history and some science they did together.
Thank you, Paulo. Well, yeah. So I did my PhD here more than 5 years ago, and you always think that you're gonna present your work, but I'm here today because John Beckman is celebrating today the 60th anniversary on astrophysics, and they told me to tell the story, which I think is the most amazing story in astronomy that I ever heard. And then a little bit of things. So this starts at the atmosphere, and that blue haze that's the atmosphere of the Earth, and from an altitude of I believe like 30 kilometers on the surface of the Earth. And you can see how thin it is, super thin. All the gas that contains there is that allow us to breathe, to live, to fly, and it would be absolutely perfect if it was just more transparent. Um, Astrophysics is bounded by the limits on the wavelength range that allows to observe the sky, and most of the telescopes are optical on the ground, are optical and a little bit of near infrared and many radio wavelengths. But if we want to go to observe X-ray, ultraviolet, infrared, or other wavelengths, we need to move our telescopes way up in the atmosphere. Because of that and the turbulence is that why we put the telescopes on higher and higher and higher mountains. Problem is we don't have mountains of 300 kilometers on the surface of the Earth, at least not in this planet. So you had to develop all these incredibly sensitive detectors very carefully, and then put them on top of explosives and hope that they don't break to send them up there. But this is something very recent. This is absolutely all the change in paradigm started with Hubble, and then now we have telescopes as complicated as JWST, and then on beyond. But before all these and all the telescopes that we had in, for example, to observe the sun, uh, people had to be clever to observe the universe. And one of the best examples to do this is the sun. I am not by any means a solar astronomer, so I would probably say something that is wrong. But the sun is, well, that's the closest star. That's not a mistake. But one of the biggest challenge to understand the sun is that how can a star have millions of Kelvin in the center and cool down in the surface at 5,000, 6,000 Kelvin, and then heat up again in the corona at a million of Kelvin again when the atmosphere is so thin. It should be transparent to the atmosphere. So that was that is still a mystery, and they're still working into that with more advanced observation from Parker Solar Probe. But before that, astronomers had to observe the corona mostly from the ground. And one of the best one of the best opportunities to observe the corona is to wait for an eclipse. That's like a natural coronagraph, by a cosmic chance that doesn't happen in any other planet in the solar system. The moon and the sun have the same apparent angular size, and sometimes the moon covers completely the sun, just allowing you to see the corona by removing most of the emission in the from the center of the star. And this is absolutely fantastic because it increased your sensitivity in the inner regions of the corona, where most of this interplay between the surface and the external regions happen. And this is a pretty recent picture, but back in the 60s and 70s, they had no idea if this was uniform or if it wasn't, if it was speculous, or how many layers in the chromosphere would be. So they were waiting for eclipses to do this type of science. In fact, they started to fly on small aircraft to get up. In Paris, there was a flight in the beginning of the 20th century, and they just got up 200 meters below the heights of Paris, but they were super happy to observe the sun just a little bit better. So they decided to start observing eclipses or astronomy. But the problem is that eclipses, they don't happen where you want to put your telescope. You build a telescope in La Palma, and if you want to wait for an eclipse to pass over La Palma, you are done. It's gonna be really, really, really hard. Plus, there is another problem, that the eclipses are really, really fast. They move across the surface of the Earth approximately twice the speed of sound. And that only gives you about 6 to 7 minutes top of totality from the ground. So if you want to observe the sun, you have only one shot, and then wait for another 18 months approximately to have another eclipse in totality. So that's a problem, because you need to move your telescope. And even if you move your telescope and the telescope goes just under the shadow of the eclipse, you only have, again, one shot, and you are still bounded by the limitations of the atmosphere. So you want to observe how the dust inhomogeneities in the inner corona play out, and thermal interplay in far-infrared. You cannot do that type of science. That's it. So this is how the story starts. In 1973. There was going to be the eclipse of the century. Why this eclipse was very important? Well, it was this eclipse was going to be a complete total eclipse. That means that the moon was close enough to cover completely the sun, so it wasn't an annular eclipse, and it was very close to the equator. And that means that the Earth catches up with the speed of the shadow of the eclipse along its trace on the surface, and basically helps you to cut up with the speed. And that means that for observers in Mauritania, Mali, up to Niger, they will be observing the totality for approximately 7 minutes. So thousands of astronomers started to plan all these trips to Africa, Brazil, and to try to observe this eclipse, because it was going to be the one hell of a shot to try to understand the corona, the chromosphere of the sun, and many other observations. Here's where it comes our hero, John Beckman. John Beckman was around 30 years old back then, and he started to think, hey, okay, the shadow moves really fast, right? And we need to move our telescope to the shadow. So we need to fly the telescope anyway. What if we take off on a supersonic aircraft, and we drill a hole in the aircraft, and we put the telescope on it, and then chase the eclipse? And if you chase the eclipse on a supersonic aircraft, you can multiply your time of observation from 5 to 7 minutes to more than 60 minutes. Back on the pillar. So that was the plan. Just chase an eclipse. As crazy as it sounds, but how you do that? Because this is the 70s. There are not so many aircraft that were supersonic. They just it was the Cold War. There were many bombers, but the U.S. was not going to lend you a B-58 to to fly your experiment. Plus, that only holds like two pilots, one bomber, one pilot. It's not really meant for astronomy, but they had the opportunity to use this, the Concorde. It was the golden age of Europe. France and Brittany were trying to build an aircraft that was going to unite in the United States and Europe in 2 hours, and but they were still building this kind of thing. Plus, this wasn't meant as Concorde yet. It was 002. It was a prototype. So this thing was still flying on testing. So John Beckman called British Airways and he said, "Hey, can we use your telescope, your airplane very, very fast to go to Africa and then fly, not one time, but many times, because we need to test it. You need to test it, put down the helium and drill some holes on the aircraft." And that's when the conversation said, "Okay, no, we are not gonna drill a hole in this experimental aircraft." And he was like, "Actually, there were many holes, like." So yeah, and the British said, "Okay." For some reason, the French agreed, and there was another team led by Pierre Lena that convinced Aerospatiale France to install 5 portholes, 4 of them for astronomy, this, and this, and then one more which was using a porthole that was already there. They had not to install another hole in the aircraft. They just replaced one by a quartz, very transparent window. And they share the portholes between 5 different teams. Los Alamos, Paris Observatory, Kitt Peak, Queen Mary, University of London, and University of Aberdeen. And John Beckman was in one of these teams. So they started to, install all of the equipment. They need to install refrigeration for the instruments, like nitrogen, helium. They need to make sure that these windows were transparent to mid-infrared, far-infrared. They need to install all the different instruments that were, all types of interferometry, photometry. Make sure that this does not overpower the aircraft. They had a limitation of 700 kilos, including personnel, equipment. Yeah, and make sure that they don't short circuit the aircraft when they are flying at Mach 2, that kind of thing. So they started doing the test, and they developed a plan. Because how do you chase an eclipse? You have to be careful to the last second, otherwise you will still have some light getting inside your instrument. And it was very, very sensitive. So they had to take off from Las Palmas. They were trying to figure out other types of runways closer, but because of the heat, that was not a good idea, because when you take off with Concorde, they spend a huge amount of fuel. Hotter than the runway, less fuel, less path that you have, and in the end, it would be a complete disaster. So they decided to take off from Las Palmas and then rendezvous with Eclipse on top of Mauritania, and then accelerate to Mach 2 up to Chad, when they will be landing in Fort Lamy. That give them around 70. The plan was 80 minutes, but they had some air going west, and they were cut off by 6 minutes in the Eclipse duration. So that was the plan. They had to fly, and now they had to ask permission to every single country in in Africa to not, interfere with the instruments and everything. Mali, Niger, Chad said okay. Mauritania said absolutely not. And they were like, why? I mean, we have everything. Like, no, because you are going to block off the sun for the experiments on the ground. And then they started like a big conversation trying to explain that the Concorde was not going to block off the sun. Plus, that was not the problem. And then they were in contact with everyone. And then they said, okay, yes, okay, you go. Okay, so they go. Plus, there was the funding. Who was going to fund everything? Well, they found out that was when they become like a symbol of how Europe and all these experiments will be flying astronomers out to explore the sun. They had no problem with the funding, but they started around 4 months before the eclipse. So they had to rush. So they basically, this is John Beckman, by the way. Look at the fashion. It's interesting. So they had to move with the telescope and basically live in the Concorde, testing with the pilots how everything worked for these 4 months. Very stressful. They met the requirements. This is one of the pictures of one of the tests. This is the cabin of the Concorde on the flight suits. The two pilots. This is this guy, tall guy, and this pilot. This is André Tucat. This is the first person to fly the Concorde, a legend pilot who took himself the plane on the day of the eclipse. And all these guys were basically making sure that they would stay on track and then the machinery and everything from the Concorde was going off well. And this is the team of astronomers. And this guy, this is John Beckman. You see everyone that's super happy talking to the pilot, to the press and everything. And he's holding this helium dewar. He wasn't relaxing at all. This was the day before launch, so they were like, oh no, the helium, we had to protect the helium. And this is a little bit of a story because they were in Las Palmas in the 73. It was basically at the end of the dictatorship in Spain, and they were in a military base. So they landed this aircraft. All these guys were, foreigners, and they had these huge storage cans of helium. They were just in the sun. So at some point, they figure out like, okay, helium is gonna boil away, and if we run out of helium, that's it, no mission. So they said, okay, we need to cover it. How do we cover it? Let's find a place to cover it, and then they found like a garage. So they opened the garage with no permission at all, and there is like a old Land Rover inside. I said, let's take this car out. Take the car out, no permission. And when they were taking the car out and putting the helium inside, some guys with machine guns were going to the astronomers, like, what are you doing? And then they were like, storing the helium. They had no idea what the helium was. Well, John Beckman this was not the last time where John Beckman was pointing with a gun. But I don't know if it was the first one, but he sure protected the helium. So just the minutes before the aircraft takeoff, this is John Beckman cleaning the window of the aircraft before takeoff. We had to say thank you for the rest of the team for remember to put John Beckman inside the aircraft before taking off. They took off at the right time, and the mission was a complete success. They started observing the eclipse at the right time. They started gathering information about the morphology in far infrared of the spicules of the sun. There was another experiment to try to figure out if it was a circumstellar disk of dust around the sun, which turned out to be variable. They even had a UFO encounter, which was solved by one of the Russian team members as a potential either a spy airplane or UFO, and turned out to be just a meteor. But apart from science, which was fantastic and only to be off by space telescopes much later in time, they basically became like a symbol. They inspired everyone, and they became the idea that the astronomers could go to space and basically to the edge of space and do science, and that this edge of space was not just meant to be broken by military guys that go to the moon and ping rocks. And this was very important also to develop what will come later, the Creeping Airborne Observatory and other observatories, which I'm going to talk about. And I'm going to show you something because the space agencies were paying a lot of attention to these guys who were doing missions on aircraft, the edge of space. And this is the 70s. This is where just right when the space shuttle and all the space lab and the International Space Station, well, it was the Freedom Space Station and then International Space Station, would start to move from the paper to reality. So they had to train astronauts. This is where I need to put the
Research Center south of San Francisco. Regular scientific flights began in 1965 when the Convair 990 Galileo paced and stretched an eclipse during the International Year of the Quiet Sun. Later, this aircraft was used for a wide variety of other applications.
Those applications were to develop that thing. That was the space shuttle. It was only on paper. And they had to train a crew. That was the beginning of the payload specialist program. So they had to basically have a way to tell scientists how to behave in a confined environment, which is completely risky. If you mess up, you die, and you lose out.
In Phase B of the ASSESS program, airborne science missions are constrained to simulate the total self-sufficiency required of these proxy payload specialists in space labs. One of the most realistic of these space lab simulations is the joint NASA-European Space Agency ASSESS mission of June 1975. During a week-long test period, the Galileo 2 represents the Space Lab orbiter combination, while a nearby complex of trailers simulates an Earthbound mission operations center. 5 men, a mission manager and 4 experiment operators continuously live and work in the aircraft and an adjoining sleeping facility while performing 5 data flights. The experiment operators selected for diversity include a scientist astronaut and a university research scientist in molecular physics, plus 2 European EOs, a British graduate student, and an infrared astronomer from ESTEC.
Say hi to Beckman.
The European Space Agency Technical Center. They must maintain and repair all experimental equipment using a standardized onboard toolkit plus spare parts and components supplied in advance. A very complex instrument on board is a French 30-centimeter IR telescope, which is coupled with a Dutch detector in one ESA experiment. Each evening, the flight crew boards the aircraft, and the simulated space lab departs for a 6-hour astronomical mission. While no attempt is made to monitor psychological or physiological factors, conditions are comparable in many ways to space labs. The adjacent living module permits the crew to concentrate on their responsibilities even during off-duty hours. During the week-long confinement, 5 successful flights are accomplished.
The whole mission consisted on flights, and when they simulate space flight, they put astronomers on top of the aircraft, they flew, simulate experiments, and then land, and then simulate sleeping in a pod, and then going back, and then that for a while, week, and then rotate. So you train also the ground segment of the spacecraft. That become to be super important for training what would later become the space shuttle program and space lab mission, International Space Station. All these ideas and the working philosophy of astronauts. It was the beginning. And it wasn't only the just training the experiment, but also the environment. And one part of the environment is the risk. And the airplane that I showed you before, that's Galileo 2. Galileo 1 was destroyed. It crashed against a P3 Orion on the same landing strip that the Ames Research Center is built on. And 16 team members died during that crash. Galileo 2 was also destroyed 10 years later on the same runway on an aircraft fire. So it was, John Beckman knew that these colleagues died before he joined the team. So it's a assumed risk that you have to take when you take part on this type of missions. And that also became part of the training sample for later missions that I will tell of. This is, again, John Beckman. We know the teams in the Galileo. And some of the team members even became continuing on this program. This is a very young Claude Nicollier, who later became part of the space shuttle program, and even he repaired Hubble Space Telescope himself. He flew 3 occasions, one of them for Hubble Space Telescope. So now we are in the 90s when Hubble flew, and thanks to one of these missions, Wildfleet Camera 3 was installed in the last of the servicing missions of Hubble. Thanks, no doubt, for all these techniques of doing science and techniques on a confined environment when you have to work with what you have. And well, thanks to that, this is the only picture I'm going to show on my PhD. You can explore the universe deeper than ever, and you can make very, very deep images like the Hubble Ultra Deep Field in this, this type of beautiful images. So now we move to the how airborne astronomy continued. The Galileo Observatory turned into the Kuiper Airborne Observatory, which turned into the Sophia Airborne Observatory. And this came later in when I finished my PhD. And I told John, hey, I want to be just like you. I mean, what do I have to do? I told him, yeah, you want to go to, if you want to apply to the NASA, I signed you a really good, motivation letter and everything. And he really did. So I made it. And when I was there, he was like, hey, I'm interested in magnetic fields, And these guys in Sofia, they have an instrument that can trace magnetic fields. So why don't you go to talk with them? And in 2019, I started working with them, trying to learn about far-infrared polarimetry. And I was very lucky enough to start working with Enrique Lopez Rodriguez right after I saw this beautiful image of the magnetic field on NGC 1068. And what you're seeing there is in brightness, you see basically the optical emission and an X-ray emission in purple. And these lines is the magnetic field inside the galaxy. So magnetic fields are there. I mean, what about magnetic fields? That's the question on every single conference, right? So what about magnetic fields? Well, magnetic fields are there. Now, what magnetic fields do? Well, the interest of John in magnetic fields come because thanks to this theory. What if magnetic fields are pushing the gas and then we don't need dark matter? This is completely crazy. I mean, because there are many other traces of dark matter, and if you do that, then you have like an excess. But still, if you have a spiral magnetic field, it can certainly add up to the rotational energy of the galaxy and should have some effect. Now there is a problem. You have ionized gas. Ionized gas condenses into stars. Stars are no longer affected by a magnetic field. So you have some kind of a magnetic field which is pushing the rotational pattern of the galaxy. Then you have some kind of a kinematic decoupling between the stars and the gas. And you should be able to detect that, right? Well, yeah, but you need to measure the magnetic field. Magnetic fields are spiral, not how chaotic they are. If they are completely random, there is no effect. So you need to trace that. So there were many projects trying to trace down the magnetic fields using radio astronomy, and many of them trying to evolve magnetic fields from the early universe. Now, magnetic fields at the beginning of the universe were like 6 orders of magnitude lower than what we see now in galaxies. So one of the problems is how these magnetic fields appear. I mean, there has to be some kind of a dynamo or something that stretches the magnetic field and make them stronger. So that's part of the question too. And certainly if you figure out how these magnetic dynamos work out, you can trace down how the magnetic fields shape and if they have some kind of effect in galaxies. Well, simulations, which are very recent, are starting to tell you that you have magnetic fields which are larger than 0. Galaxies have larger disks. However, some others tell you the opposite. If you have magnetic fields that are very large, galaxies compress. So it's just to give you an idea of how difficult it is to do science in this. This is in diapers. We are still working through that, and we have very, very, very few observations. So we moved into the observations, and we started working with the Sophia Hawk team, which basically Hawk is a far-infrared polarimeter. It's 32 pixels that basically like antennas, semi-antennas, which move on the sky and try to trace the polarized emission of far-infrared of the dust in galaxies. And if you do that and you compare with the magnetic field that cannot be observed in other wavelengths, which basically is the radio wavelengths. In radio wavelengths, you can also observe magnetic fields, but the problem is that they give you the diffuse warm gas. If you are interested in the decoupling of stars and the star formation process, you have to go to the molecular cloud. It's like looking at these two types of clouds. You have this cloud, this is not going to rain. This is going to rain. If you have molecular clouds, it's going to rain stars. So you need to look at these stars. The problem is this only emits in far infrared. This emits in radio. So we had no way to do this from the ground. You need to go to far infrared, either space or the stratosphere. How this works? Well, you have dust that is rotating in space because of radiation, and then you have a magnetic field which aligns them in one direction. So the emission, which is polarized, is perpendicular to the magnetic field. You only have to turn 90 degrees, and that's it. You have the magnetic field. The problem is that you have to take off over 99.9% of the atmosphere. That takes a lot of fuel, but you can do that with SOFIA. So I had the opportunity to fly with them last year. It was very close to the end of the mission. I was super lucky, and you know how lucky I was because back then I was part of the astronaut selection program from ESA, and I was in the medical selection in Germany, and then they called me, hey, do you want to fly in SOFIA? You only have to, drive down to the desert and and do the medical training and the egress training, and that'll be it. And it's like, yeah, I'm in Germany. Can you hold for some hours? So I went there. I took on my 30-year-old car down to the desert, and I did the training, and I flew with them, and it was an amazing. It's this machine is just crazy. I mean, the way that this is the back of the airplane. This is where the telescope is. Now it's pointing in this direction, and when you are in the center of the airplane, and airplanes got bumps, but this has like, I think 32 actuators, which are acting like less than half a millisecond fast. And when you catch a bump, the telescope stays in space. So you see the bumps, and the telescope is just standing, moving on the floor. It's just amazing. The whole aircraft inside is hollow. I mean, they don't have any normal seats. They are consoles with the director, operations. The back there was the instrument team. In this direction is guidance, and then they have the one or two team members, which are basically making sure that we don't cross in any military space, or move down to Mexico because there is some kind of airflow moving in that direction. If you do any of that, you have to close the dome and then fly away, which takes half an hour and a ton of fuel. And then the best part of the night is when this aircraft is full of fuel. It's a 747, it's a little bit modified, but in the beginning it's just too heavy to fly really, really up. So as farther you fly, less fuel that you have, the higher you can go in the atmosphere. So the best object of the night is reserved for the last part of the night, and that's the most, right before dawn, you are observing, and then you go very, very, very fast. So we did that, and we started observing this type of galaxies. Again, this is M51. This is the first paper of the Salsa Legacy team, where we presented all this project, trying to measure and quantify all the magnetic field of spiral galaxies, and because we needed to compare it with previous observations. So now the problem is, okay, we have the data, and now we need to try to understand how this mess of wobbly magnetic field lines and behave, and what kind of information can we extract from that. So now the idea is, okay, we need to compare the magnetic field from far infrared polarization, which is this, with previous observations on the synchrotron polarized radio emission, which again traces the magnetic field in the halo of the galaxy. So how can you do that? Well, you need to measure how spiral these fields are. So we figure out that we can use only one parameter, the pitch angle. If you have a field a spiral field with a very low pitch angle is almost circular, like this one. You have a field with a very high pitch angle. It's like this one, almost radial. So if you fit the whole field to these things, you can compare both the spirals in a quantitative way. We did that, and I'm going to show you only this plot. I think it's the first scientific plot I saw in the in the whole talk. In the x-axis is the distance to the galactic center in arc seconds on M51, and in the y-axis is the pitch angle. You know how loose the spiral is or how tight. So it's very close to zero. This is almost like a circle. If it's going up, it's completely radial and open. Okay. Now we are going to plot the magnetic field of radio polarization. This is from the ground. This was obtained in the 90s, I think. Nothing in particular. A spiral which is almost constant, around 20, 30 degrees in magnetic pitch angle, which is, you know, normal spiral. And if you observe this in far infrared, you see that the magnetic field is roughly the same up to a certain radius, and then it breaks. It's like if the spiral had an elbow, like a yeah. Okay, so what does it mean? You have a magnetic field which is distorted, but you only have one magnetic field, right? You can only have one magnetic field in a given moment and space. So this is the proof for the first time that our idea that the radium far infrared was observing different layers of the same galaxy. Now you are seeing different regions of the same galaxy using something that is not directly light. It's the magnetic field. You are dissecting the layers of the galaxy. You have the magnetic field of the halo, and then you have the magnetic field in the inner equator of the galaxy. If you do that for different arms, you obtain different different magnetic spiral arms for the both arms of M51, and this is a consequence that M51 is interacting. And what happens when galaxies interact? When I don't know if you have seen many simulations, but one consequence when you have merger or minor merger or major merger is that the molecular clouds and the diffuse gas detach completely. Then the angular momentum goes down into the molecular cloud, which compress, form stars super really fast, and they go to the center of the galaxy, and the diffuse gas expands and catches the angular momentum. So if you do these simulations in M51, you see that this is expected. The outer regions should, go down to the center of the galaxy. This is a consequence, and which can also be observed in by using corrotation methods in H-alpha. Okay, so now we have one galaxy. It's amazing. We use all this kerosene to observe one galaxy. That's a lot of science. So now we had to do more. We need more. We fly more often, and we started observing more galaxies. And we observed NGC 6946, which is the firework galaxy. This galaxy has a very chaotic magnetic field, which correlates with the star formation rate. It's basically like more strength on the magnetic field, more star formation. You have galaxies like Centaurus A, which trace completely the jet in perpendicular to the direction of the disk, like M82. 2146. This is a very interesting object that it's very hard to see here. I will send you the poster, but you see that the magnetic field, it's when you observe in different wavelengths, you can see how you can trace in the longer wavelengths. You observe the outflow, and in shorter wavelengths, you observe the disk. And it's another way of dissecting. It's just like light, but with magnetic fields, and so on. So we observed 14 of them. Yeah, this is some summary. As a conclusion for the whole program, and this will be the last slide, and far infrared is more effective in detecting the magnetic fields along the galactic outflows. And that means that we are observing how these jets are dragging down the magnetic field from the inner part of the galaxy to the outer fields, generating this X shape, which are very, very characteristic. In spiral galaxies, what you get is that far infrared is more chaotic and more turbulent than synchrotron emission. And that again is a consequence of being observing the molecular clouds. This was a theory. We were trying to observe the dust emission, but that was in theory. When you observe this and then you figure out that there is a detachment between the halo and the far infrared, which is traced by the molecular clouds, and you obtain different magnetic fields, you have living proof that you are observing different regions of the same galaxy. So having a magnetic field which is more turbulent in molecular clouds, that's expected because you have, activity, supernovae, and all the outflows that appear when in regions with high star formation rate. So what's the final conclusion of this paper? And these two papers. So I will finish here my talk. The SOFIA program finished last year, sadly, because we were at the peak of the publication rate, but here's how things are. But also the Galileo 1, Galileo 2 were destroyed. Kuiper Airborne Observatory, George Park in the same runway that SOFIA is, and still there were missions after that. So we are hoping that in the future we will have some other missions to replace this one, and we will be ready. Well, thank you.
Alex, it's time for questions.
Yeah, my question is just where you will have finished. Sophia was the commissioner, so, and if these are realistic plans for new missions in planes or orbital platforms, another one to continue your work?
This is my opinion, not NASA.
Yeah, I know.
But Sophia was 50% a laboratory and 50% science. When they decommissioned Sophia, they were measuring Sophia against missions like Hubble. That's what happened in the decadal that was in 2020. So when you measure an optical telescope, which was invented by Galileo, against a far infrared technology like this one, which are measuring the phase of every single photon that arrives to the telescope, is not fair. This telescope was developing the technology that will later become missions like PRIMA, which has been proposed. It's a far infrared polarimeter that will be sent to space in I think it's a 2-meter telescope. This is a proposal. For now, I think that the decommissioning of Sophia was too early because we need to test the equipment, we need continuity, and in the end, we are people. When you go to Armstrong and you meet all the engineers and scientists that are working in this airplane, you met 150 people with their families that live in Palm Bay, and all these people are now working in something else. If you want to develop, even if you want to restart this mission, you have to bring them back. And that's the problem with projects. There are people behind. You can put the money and take it out and put it back. The people are gone. Expertise is gone. You need continuity. So if you want to restart this mission, even as a space telescope, you will need to transition from this to the next mission. If in 5 years, PRIMA is approved, funding is unlocked, people can start to work, you can move all these people and equipment to the next mission, but not now. Still, we have to live with the tools that we have, and we will try to continue, but that's the point.
Thank you. Very, very wonderful talk. Thank you so much. And also, congratulations for your work on magnetic fields in M51. Very, very interesting. I'd like to know a little bit more, if possible, about the cost operations of the SOFI project. But apart of that, something that really brings my attention is you said that John was negotiating with British Airways about how to use this new legendary aircraft. But it wasn't a success. And then Air France really accepted the proposal. Actually, John was a British citizen, subject of the of the Elizabeth Queen. How do you know a little bit more details about the negotiation, how it was? Because at that time, Air France was a fully public company. So I guess this is something that politically you have to discuss first. So how was this, if you know a little bit more about how he managed to really get the agreement with Air France?
Well, the agreement with Air France, I mean, they started with another scientist, which was doing all this idea in parallel. So many astronomers figuring out that supersonic aircraft was the solution. So there was another astronomer called Pierre Lena, who I think he started the conversation with actually with the pilot. It was the test pilot from the Concorde program. They just met, have some coffee, and draw in a paper the idea, and he was like, Turcat was amateur astronomer himself, and he said, "Wow, this is super cool," probably in French. And so when Turcat was this guy, so he had some hand to convince Aerospatiale. About the British part, I had no idea. And we are very lucky that Johnny is right there and we can ask him today. So I think that we can ask some questions about how many holes they had to drill and how they take it out. I think that in the conversation they thought that they needed the okay, this is a little bit of story here. Concorde was being used at the time for observing the amount of ozone in the atmosphere. So this was, in the 70s, people were thinking that, we were going to be living in Mars. And they thought, okay, New York is going to be 1 hour from Paris in very few years, and we are going to have like 1,000 Concordes flying up. But these aircraft consume a lot of fuel. And when they were flying, they were emitting, I think, complex molecules of nitrogen. Ernest, you were saying yes, so I think that you know the story. Okay. Yeah, these consume a lot of fuel, and they fly really high up, where just the ozone layer is. And there were some scientists saying, "Hey, maybe we should think about putting 1,000 Concorde flying every single day, because we are started to notice a decline in the ozone layer." So one of these Concordes was used. I think there were both of them to install instruments in the side windows, which were already there. And that was not a problem. Like, okay, we change one window by another window and you install your instrument. That's okay. But they did not understand that they had to make a hole in the roof, which is different. And when they figured out that out in a couple of meetings, they said, no, sorry, it was way too much uncertainty.
Yeah.
But I guess that the details are probably John.
Yeah.
We said.
Yeah.
And
this story about the Concorde is awesome. Actually, to the best of my knowledge, I think the very last flight of the Concorde, it was also like chasing a solar eclipse after this, sadly, Air France 4512 in Paris. And actually, I didn't know that story about John, about the first really scientific flight of the Concorde. But the point is, they finished doing also the same, chasing a.
Yeah, but still, John holds the longest and fastest eclipse record from all time. I think that the latest flight that they did to an eclipse was like
Few minutes.
few minutes.
Yeah, it was for rich tourists, no more.
People.
Yeah.
So,
but it's a historic curiosity, I think.
Yeah.
Thank
you. I remember to hear John talking about the history, and they say that the pilot put the plane to the limit. They was absolutely pushing the plane to the Mach 2 point. Forcing the engines. Yeah. To try to get the limit and to extend the duration of the eclipse.
I think that in the PCR record it was like 2.8, I think, Mach, and then they went to the best measurement that they had of the duration was because John was coursing at the beginning, at the end, and they had a recorder, so they had the most precise recording of when the the eclipse started and finished. And then they figure out that the Mach should be longer. So it was like a background investigation, and they figured out that the panel was pushing a little bit the aircraft. Yeah. It's completely insane. That's why I like this talk, because it's insane.
Hello, thank you for the talk. Regarding with the magnetic field, you were saying that the magnetic field correlates strong with the star formation. And I'm wondering what happened with in the passive galaxy. Like, do the magnetic field just disappear, or how is do they follow a pattern, or what happened in do you know?
That's a very good question. And I don't think that we had the answer, because
Yeah, what do you
we have,
think that, I mean, in theory?
we have very few observations. And the one thing that you can measure with the galaxies that we have, bring down the slide, but is that you can measure how chaotic the dispersion of the magnetic field. You have the spiral. You subtract the spiral, you have some kind of a measurement of how deviated is the magnetic field. If you measure that deviation of the magnetic field and you correlate it with the star formation rate, you obtain some correlation.
The more chaotic, the more star formation you have.
Yeah, but that's rather a consequence, because the supernovae and even the compression twist the magnetic field. So you don't.
Yeah.
Is the magnetic field which is influencing the star formation rate, or is the star formation rate which is shaping the magnetic field? That's pretty hard. When you go to the measurements on the Milky Way, so I think I have one picture here. You can measure that there is an interplay between the compression of the filaments. This measurement, basically you can measure how parallel the magnetic field lines are to the filaments, and make a plot in terms of density. So what you see in filaments in the Milky Way is that you have magnetic field, which is not super strong, and then you go to a very dense region, and the magnetic fields collapse with the gas, because in the end it's gas, it's frozen in the magnetic field. So when they collapse by gravity, they drag down the magnetic field lines. But when you put magnetic field lines together, magnetic field increases. So it's the magnetic field who brought the filament together, or it is the gravity who brought the filament together. So it's kind of hard. It's an interplay. It's for example, something that can be measured, and when you're trying to form new stars, you need one of the problems is that they spin way too fast. If you don't include magnetic field, the stars start spinning way too fast to compress, and the star formation rate would be way lower. So when you add magnetic field, you start adding some dissipation of the angular momentum, and they start forming stars faster. But if you have magnetic field way too strong, the filaments don't collapse. So it's like it's like an interplay, and it's really, really, really hard to measure because we don't have Sophia anymore.
Okay.
So yeah.
Yeah, it's a tricky question.
It's a tricky question.
Yeah. Well, thank you anyway.
Yeah, the operation. Well, I think Sophia was as costly as Hubble in terms of year by year operation. Half of the cost was in fuel, so it was burning. That was one of the arguments to shut down Sophia, because it was very costly. Again, I think that it's comparing apples to oranges. Nobody compares a big laboratory. Nobody compares a particle accelerator to Hubble. Why? Because, well, particle accelerators are also technical development, and you need that technical development is way more costly than the final product. Hubble is, in some sense, a product, like James Webb. And if you build a second James Webb, it would be 10% the cost. And if we were building James Webb's every single day, it would be like super cheap. The first one is really, really costly. And Sophia, it was exactly the case. You were testing equipment that was, you fly, it breaks, you go down, you replace the equipment that you need, you refuel, you go up. I think, and this is super personal, that we are bounded by a philosophy of, trusting equipment. Like, oh no, it's way better to just dump a telescope, make another one, and launch it to space. Well, that's okay. Yeah, it's cheaper than trying to repair James Webb. Like, for example, if James Webb was broken, it couldn't open the mirrors. They just, okay, that's it, out, not a problem. But we need to think in the longer term. And this is personal, but it's a little bit of philosophy. If at the same time we are telling the community that we are going to Mars, do you really think that we are going to Mars and nothing is going to break in the way, in an 18-month mission? People, yeah. I mean, if we are going to Mars in 18 months, something is going to break. And if you think that nothing is going to break, you have never been in camping. So when people went to Hubble to repair Hubble, they were not just repairing a piece of equipment. It was probably cheaper to launch another space telescope. I mean, these space telescopes, Hubble was approved really fast because there were like 10 or 12 SpySats with the same class looking down on the Earth with the same capabilities. Just another one. Super cheap to launch another one. When they were doing this, they were not doing this because of there was not another way. It's the only way to learn how to do this. I mean, developing a robotic arm that you can put an astronaut on board, developing the globes for astronauts, tools that they need to compensate the momentum because otherwise you rotate with the tool. All these communication systems, the payload bay from space shuttle, all the equipment to bring down. Hubble was going to go down every 3 years to Earth, install new instruments, and then fly up. All this technology was developed because of this. And this is why International Space Station works. And if you don't add up the long future to the equation, then nothing of this makes sense. Yeah, it's cheaper to launch another telescope. Also, it's cheaper to not launch anything and continue working in other stuff. That's not why we do things. We do things because we think of the future. And this is the future. Not launching another stuff. Reusing is better than recycling, and repairing is way better than both, right? Same thing.
We're running out of time. Thank you, Alex, again.